basis of V, and let the set A, which is equal to y1, y2, y3, ym and ym plus 1 be any ordered subset of V. Now the question is, what will be the nature of A? Whether A will be linearly independent or a dependent. Now, as we know that this A is a non-empty subset of a vector space V. That means this vector y1 will be the element of V. As we are given that this B is a basis, hence we can say that the span of B is equal to V. Now, as we are given that this vector y1 of A, and A is a subspace of V, that means definitely vector y1 is a vector of V, and V is equal to span of B. That means this y1 will be the vector of span of B. And as we have discussed previously, so the set y1, x1, x2 up to xm will be linearly dependent set. So definitely this set, say this set is A1, then definitely this set A1 will be a linearly dependent set, because we know that now this contains y1 is a linear combination of x1, x2, x3 up to xm. So A1 is a linearly dependent set. Now we can find if A1 is a linearly dependent set, then any vector except this first vector, we can find any vector xi in A1 such that xi can be expressed as a linear combination of the vectors preceding xi's. So say xi vector can be expressed as a linearly combination of its preceding vectors, and if we remove xi from this one, so if we can remove xi from A1, and if we define this set as S1, then S1 is equal to y1, x1, x2, xi minus 1, xi we have removed, so xi plus 1 up to xm. This set will have exactly m elements, and now this will be a linearly independent set. So we can say that the span of S1 will be equal to V. Again, we know that y2 belongs to V, and V is equal to span of S1. That means definitely if we include y2 in set S1 as this one, say y2, then y1, x1, x2, xi minus 1, xi plus 1 up to xm, and if we define this set as A2, then again A2 will be linearly dependent set. Again, as this is a linearly dependent set, we can find any vector. So there exists some vector xj in A2 such that this xj can be expressed as a linearly combination of its preceding vectors. And again, if we can remove this xj from A2, and if we define a new set as S2, which is equal to y2, y1, x1, x2 up to xi minus 1, xi plus 1, xj minus 1, xj plus 1 and xm. The second possibility is also that whether y2 is a linear combination of y1. If it is so, then this is linearly dependent. If it is not, then we can find this xj from this one. And after removing the xj from this one, now this S2 will be linearly independent and the span of S2 is equal to V. If we continue this process for m times, then we get Sm will be as ym minus 1, ym minus 2, y3, y2 and y1. And definitely this Sm will be span V. So we say that this Sm is a basis for vector space V. Again, say ym plus 1 is any vector of V and V is equal to span of Sm. That means definitely ym plus 1 belongs to the span Sm. And when ym plus 1 belongs to the span of Sm, then the set am plus 1 will be like that. Ym plus 1, ym minus 1 up to y2 and y1. And as ym plus 1 can be expressed as a linear combination of Sm, this set is definitely a linearly dependent set. And as a previous one, we have think that the set y1, y2, y3 up to yn plus 1, we have supposed that this is a linearly independent set, which is wrong. Hence, any set containing m vectors in a vector space whose dimension is containing m vector will be definitely a linearly dependent. So, if in any vector space V, if basis of a vector space contains n element, then in that vector space any subset containing more than n vectors will definitely be a linearly dependent set. Now let us think about that. In any vector space, let V be a vector space and say B1 and B2 are two different bases of vector space V. If B1 is a basis, B2 is a basis, can B1 and B2 have same elements? Can they have different elements? Let us suppose that B1 is a basis of V with m elements and say B2 is a basis of V with n elements. Then what can we say about m and n, whether they are equal or not equal? That's a question. Now let us think. B1 is a basis of V. That means definitely span of B1 is equal to V and B1 is linearly independent. Same way, B2 is a basis. That means span of B2 is equal to V and B2 is linearly independent. Now say B1 is a basis and consider B2 is linearly independent set. What can we conclude from this? We know that basis contains the maximum number of linearly independent set and the number of elements in basis are m, and number of linearly independent vectors in any set are always less than or equal to the number of vectors in a basis, and B2 contains n elements. This will implies n will be always less than or equal to m. Think different way. say B2 is a basis, and consider now B1 as a linearly independent set. Okay, B2 is a basis. This contains exactly n elements. B1 is a linearly independent set. Therefore, the number of vectors in any linearly independent set must be less than or equal to number of vectors in basis. Here B1 contains m vectors, so number m will always be less than or equal to n. N is less than or equal to m. M is less than or equal to n. This will give us m is equal to n. So if we take two different bases of any vector space, then the number of vectors in any vector space are always same. So two things we have conclude. First, any vector space may have more than one basis, and second thing, any vector space which have more than one basis but all the bases have same number of elements in it. And now we'll say that the number of elements in any basis are called the dimension of a vector space. So the number of vectors in a basis is called the dimension of a vector space V. And if this number is finite, then we say that that vector space is a finite dimensional vector space. And if this number is not finite, then we say that the vector space is an infinite vector space. And if we consider any polynomial, set of polynomials, then we know that if we have a polynomial of n degree, then we may have 1 x, x square, x cube up to x raised to n. And we can say that with using 1x, x square, xn, we can generate any polynomial of degree n. But if we consider any polynomial without defining any degree, then this basis will be an infinite number of elements in basis, and that's why we get that any set of any polynomial is an example of a infinite dimensional vector space. Now, in a vector space, suppose we are given that, so we know that now if R1 is a vector space, its dimension will be 1. Dimension of R is 1. In R2 is a vector space, we know that the basis of R2 is 1, 0 and 0, 1. So number of vectors in that basis are 2. So the dimension of R2 is equal to 2. In R3, we know that the basis for R3 is 1, 0, 0, 0, 1, 0, 0, 0, 1. This is standard basis for R3. So the dimension of R3 is 3. Now, suppose we have given a vector space Rn with dimension n, and suppose we have given that in this vector space a non-empty subset, non-empty linearly independent subset of this Rn with less than n element, then we can expand or extend this set up to the basis for Rn. Suppose we are given that, say 1, 0, 0 and say 0, 5, 1. Suppose this set A is a linearly independent subset of R3. Now, can we extend this set up to the basis of R3? We know that only linearly independenceness is not important to define a basis. We must have span of A, whether this is equal to R3 or not. This is our question. And if span of A is equal to R3, then definitely A will be a basis, and number of elements in A are 2. It may be possible that if we can show that this can expand this up to R3, then its dimension will be 2. Otherwise, we have to add some vectors in that set. So for A, if we take the linear combination of vectors of A, Vectors of A are 1, 0, 0 and 0, 5, 1. And the linear combination of A, that means the span of A, will be alpha 1, 0, 0 plus beta 0, 5, 1, where alpha and beta are arbitrary, any real number. So span of A will be of the type alpha, 5 beta and beta. Now if we take alpha is equal to 0 and beta is equal to 0, definitely we will have a vector 0, 0 and 0. And if we change a slight coordinate, if we change these two coordinate by different one, if we take first element any arbitrary, say 0, if this is beta, then this will be 5 beta. So we will select such coordinate which cannot be in the span of A. So if I take 1 here and if I take 5 here, then this will be the same set of this one. If I will take 2 here and 5 to the 10 here, then it will be in the span of A. But instead, if I take 1 here and 2 here, then definitely this set will not be the part of span of A. And definitely the set 1, 0, 0, 0, 5, 1 and 0, 2, 1, this will be the basis for R3. So we have extend this to set A up to the basis of R3. There are so many examples. Let us consider vector space R4. And let us take an example. S is equal to say 2, 3, 0, 0, 5,